Welcome back to another deep dive into the world of biochar. We're tackling the hottest topics straight from biochar today, and let's just say, things are heating up.
It's an exciting time to be following biochar research, that's for sure.
It is. And this week, the top story, drum roll please, is all about wastewater treatment. Biochar as a game changer in sustainable wastewater treatment, a 2024 retrospective and future outlook. Catchy title, right? But seriously, could biochar be the answer to the global water crisis?
Well, it definitely has the potential.
I mean, turning waste into a water purifier, it's like alchemy almost.
Yeah.
But obviously there's some serious science behind it.
Right, and the key is biochar's structure. It's incredibly porous, think like a sponge, but on a microscopic
A
level.
super sponge.
Exactly. This porous structure gives biochar a massive surface area, which is perfect for it.
Trapping pollutants.
You got it. And not only that, it also has these things called functional groups.
Functional groups.
Yeah. They're kind of like tiny chemical hands that grab onto all the bad stuff. We're talking heavy metals, dyes, even things like antibiotics.
Sounds like a super sponge with sticky hands.
Pretty much. And the research coming out is really promising. The article highlights some breakthroughs from 2024, like removing 80% of cod and a whopping 90% of antibiotics using magnetic biochar.
90%. That's incredible. Wait, magnetic biochar?
Yeah. It's biochar that's been, you could say, enhanced. Scientists are finding ways to modify biochar to make it even more effective. Magnetic doping is one technique that's creating a real buzz.
So instead of complex filtration systems, you just use a magnet to pull the biochar and all the pollutants that's collected right out of the water.
Exactly.
That is so cool. And magnetic doping isn't the only trick up their sleeve, right?
Right. There are other surface treatments that can boost biochar's absorption capacity, its pollutant grabbing power, if you will. Some treatments can even give biochar catalytic properties,
Catalytic, meaning...
meaning it can actually break down contaminants, not just hold on to them.
Wow, we're talking next-level water treatment here. The article even mentions biochar being integrated into systems with adsorption, photocatalysis, and electrocatalysis.
It's pretty cutting-edge stuff, but scaling these innovations from a lab setting to a real-world wastewater treatment plant is a whole other challenge.
Right. I imagine things get a lot messier out in the real world. But hey, at least sourcing the biochar itself seems pretty straightforward.
Yeah, that's one of the biggest advantages.
Transforming agricultural and forestry residues, basically stuff we normally just throw away,
Yeah.
into this wonder of it. It's like the ultimate upcycling project.
Exactly. Biochar production addresses waste management and environmental remediation at the same time.
Talk about a win-win. And this isn't just about, like, cleaning up random dirt, right? We're talking about stuff that's seriously bad news for our water. Antibiotics, heavy metals, endocrine disruptors.
Right, things like BPA. These contaminants pose serious threats to both human health and ecosystems.
Absolutely. And the article highlights how researchers are using tools like bibliometric analysis to map out the research landscape, ensuring that,
That future studies are laser-focused on the right areas.
Exactly. So what's next? What are some of the hot topics in biochar research right now?
Well, besides figuring out how to scale up these lab discoveries, there's a lot of excitement around nanocomposites.
Metacomposites?
It's about combining biochar with nanomaterials to create, think of it like,
Microscopic pollutant magnets?
yeah, something like that. And then there's surface functionalization. It's
Okay.
essentially tailoring the surface of biochar with specific molecules to target very specific pollutants.
Like a custom-made pollutant trap. The article also mentions using machine learning in biochar research.
Oh yeah, machine learning and modeling are becoming super important. Imagine predicting the perfect biochar properties for different types of wastewater or being able to,
Model how biochar will interact with specific pollutants.
Exactly.
That's amazing. It sounds like we're on the verge of a biochar revolution.
Yeah, we might be. But it's important to remember there's still challenges to overcome.
Oh, definitely. Scaling up is a big one. Taking something that works perfectly in a lab and making it work on a large scale in a real-world wastewater treatment plant is a huge hurdle.
Absolutely. And then there's the cost factor. For biochar to become a mainstream solution, it needs to be economically viable.
So cheaper and more efficient production methods are key.
Yep. And we can't forget about consistency. Not all biochar is created equal. Standardizing production and characterization is crucial to ensure consistent quality and performance.
Right, because you don't want to end up solving one problem only to create a new one.
Exactly. And that's why researchers are actively investigating the potential for,
Secondary pollution?
yeah, things like metal leaching from the modified biochars and any harmful byproducts that might be produced during treatment, sustainability is about the big picture.
Absolutely. And speaking of the big picture, we need to remember that real-world wastewater isn't like a neat little lab sample. It's a messy mix of all sorts of contaminants,
Right? It's a complex cocktail of pollutants, and understanding how biochar performs in that kind of environment is crucial.
which leads us to a really exciting possibility, in situ remediation.
Ah, yes. Using biochar to clean up polluted water bodies and soils directly.
It's like instead of digging up contaminated soil or pumping out polluted water, you just use biochar to clean it right where it is.
Precisely. And that actually ties in perfectly with our second story today, which focuses on.
Biochar's ability to remove those pesky organic pollutants.
Let's dive into that.
So this second story, biochar for water pollution remediation, opportunities and challenges, dives deep into these organic pollutants, those PAHs and pesticides everyone's talking about.
Yeah, these are some of the toughest contaminants to deal with.
They really are. And this article, it highlights how effective biochar can be.
It does. It even mentions a study from just last year, 2025, by Belgian and his team, published in Nanomaterials.
Yeah.
They found that biochar could remove over 90% of these organic pollutants in, well, lab conditions, of course.
90%. That's amazing. But how does it actually work? What's the secret sauce here?
Well, it's not really a secret, it's science. Biochar has a few tricks up its sleeve when it comes to these organic pollutants.
Okay. I'm all ears.
The first one is something called hydrophobic interactions.
Hydrophobic meaning.
Water hating. Basically, these organic pollutants, they don't like water. They're kind of like oil in that way.
Right. Oil and water don't mix.
Exactly. But they're attracted to biochar, so they tend to stick to its surface.
So it's like biochar is giving them a place to hang out where they feel more comfortable.
You could say that. Then you've got hydrogen bonding, these weak bonds that form between the pollutants and the biochar.
So they're not just hanging out, they're actually getting attached.
Exactly.
Yeah.
And finally, there are electrostatic attractions.
Which are?
Think of it like static cling, when things with opposite charges stick together.
Right.
Sometimes biochar and the pollutants have these opposite charges, so they're drawn to each other.
So it's a triple threat.
Right.
Hydrophobic interactions, hydrogen bonding, and electrostatic attractions. No wonder those pollutants don't stand a chance.
It's a pretty powerful combination. And when it comes to those PAHs, the article mentions that high-temperature biochars are especially good at grabbing onto them.
Why is that?
It has to do with these things called pipe interactions.
Pipey interactions.
Yeah, it sounds complicated, but it's basically like, imagine PAHs and high-temperature biochar having these special zones, like magnets.
Okay.
These magnets are actually electron clouds called pi systems, and when they get close, they attract each other.
So the high-temperature biochar is like a supermagnet for PAHs.
Exactly. And for pesticides, researchers are getting even more creative. They're engineering biochars with tailored surface modifications.
So customizing the biochar to target specific pesticides.
Yep. It's like designing a custom-made trap for each one.
That's incredible. Biochar really is a versatile tool. It can be used for treating municipal wastewater, industrial runoff, agricultural drainage. It's like the Swiss Army knife of water treatment. But as we talked about before, scaling up these solutions from the lab to the real world always comes with its challenges, right?
Definitely. And this article does a good job of outlining some of those.
Like what?
Well, for one, the environment itself plays a huge role. Things like pH levels, competing ions in the water, even the amount of organic matter can all impact how effectively biochar can absorb those pollutants.
It's like trying to clean up a spill in a room where everything's constantly moving around.
Exactly. And then there's always the cost factor. For biochar to be widely adopted, it has to be economically viable.
Right. We need to be able to produce and use it in a way that makes sense financially.
Exactly. And then there's consistency. Not all biochar is created equal. Inconsistency in the biochar itself can lead to variations in performance.
Right. And you need reliability when you're dealing with something as important as water treatment.
Absolutely. And then there are logistical things to consider, like transportation and distribution. Getting the biochar to where it's needed efficiently and affordably, that's another hurdle.
It sounds like a lot to consider. The article also mentions some concerns about those modified biochars.
Oh, yeah. There are definitely things to consider there.
Like what?
Well, those complex manufacturing processes, they can be expensive and they might have a bigger environmental footprint.
Right. Sustainability is about the whole picture.
Exactly. We have to weigh the benefits of enhanced performance against the potential downsides of more complex production methods.
So where do we go from here? What's next for biochar research in this area?
Well, one promising avenue is combining biochar with other treatment technologies.
Oh, interesting. Like what?
The article specifically mentions advanced oxidation processes, or AOPs, and microbial treatments.
Okay, I'm not familiar with those.
AOPs use powerful oxidizing agents to break down pollutants, and microbial treatments use, well, microbes to degrade those contaminants.
Oh.
So imagine using biochar to first capture those pollutants and then hitting them with AOPs or microbes to finish the job.
So it's like a 1-2 punch, right?
Mm.
Capture and destroy. Biochar grabs those pollutants,
Yeah.
and then the AOPs or the microbes come in to finish them off.
It's a powerful combination. And this idea of combining different approaches, that's definitely a key area for future research.
It makes sense, using the best of each technology.
Exactly. So, we've covered a lot of ground today, from those amazing absorption capabilities of biochar to all the challenges of scaling up and real-world applications.
We really have. It's been fascinating. But big picture, what's the main takeaway for our listeners today? What should they be thinking about as they go about their day, after listening to all this?
I think the biggest takeaway is hope. I mean, biochar really does offer a promising solution to some of our most pressing environmental challenges.
It does, especially when it comes to water.
Right. And not just cleaning up water, but doing it in a way that's sustainable, in a way that closes the loop and turns waste into a valuable resource.
That circular economy in action.
Exactly. And it's not just water. Biochar can be used for soil remediation, for carbon sequestration, even as a soil amendment to help grow more food.
It's amazing how versatile it is.
It is. And the research, it's just exploding. All these innovations we talked about, engineering biochar for specific pollutants, combining it with other technologies, it's all pushing the boundaries of what's possible.
It's exciting to think about where all this could lead.
It really is. But we also have to remember that there's still work to be done.
Definitely. There are those real-world challenges, the scaling up, the cost-effectiveness, all that.
Exactly. So optimizing production methods, ensuring consistent quality, figuring out how biochar performs under different environmental conditions, those are all key areas for ongoing research.
It's like biochar is on this amazing journey, and we're just starting to see its potential unfold.
That's a great way to put it. So to leave our listeners with something to ponder today, maybe this. We've talked about how biochar can clean up pollution and contribute to a circular economy, but what if we take it a step further?
What if we?
What if biochar could be the key to a truly regenerative approach to water management? One that not only cleans up existing pollution, but actually enhances the health and resilience of our water ecosystems. Something to think about.
That's a great question. And on that note, thanks for joining us for another deep dive into the world of biochar. Until next week, keep exploring, keep asking questions, and remember, the future of water might just be a little bit charcoal-colored.